Last class, we discussed Marxist model of economic growth based on some observations regarding to economic growth facts, but those facts are for the period before 1800. Remember, so before 1800, along human history, there wasn't much growth in terms of standard living, and also there wasn't much growth in terms of population. And Marthos developed a model to explain why this is the case, right? So now we are going to move to modern economic growth experience. Essentially, there's a sustainable continued growth every year. Okay? And then, so in today's class, we are going to rest on a solo growth model. This is named after a Nobel Prize winner, and he developed a growth theory that accounts for the stylized facts, what we observed after 1900 or after Industrial Revolution, right? After that, so we are going to use this model to do some growth accounting. Essentially, the growth accounting is used to understand the source of economic growth or the contribution of each factor that can potentially promote economic growth. So what is solo growth model? So this model, first of all, this model has become a bare bone or becomes a workhorse for modern theory of economic growth. Right? So this was invented by Solow. As I said, so he was a Nobel Prize winner. A key prediction of this model is that technological progress is necessary. Okay? So technological progress is necessary for sustained increase in standard living. Right? So standard living usually is measured by output, like we discussed last time, right? Okay. So to appreciate the importance of this model, or maybe the need for a model, now let's look at some stylized facts or like case study. In 1960, there are two countries. One, South Korea, the other is Philippines, right? Both in the Asian country. In 1960, these two countries are very similar. Okay? They are similar in many metrics. Start with standard living, per capita GDP. So they're very close, like 1800 versus 2200. Right? So actually, Philippines is slightly doing better. Population, both countries has about 25 million, right? And among these 25 million, around half of them are working age, very similar. Now, in terms of sectoral composition or in terms of industry, right? So they're also similar. So both have certain fraction of industry and agriculture. And then finally, in terms of college enrollment, as we're going to see later, this is a very important factor in growth. Right? This is a measuring of human capital, also as measuring of technology, so on and so forth. Right? It's because the more college students you have, and then the better educated of your workplace, more efficient they are, higher productivity they have. Okay? Korean, the enrollment rate is 5%. Philippines is more than double. Okay? To summarize, in 1962, these two countries are similar, but in some sense, Philippines is a little bit better. Right. Now, since 1960, so if we just look at 2007 or even today, these two countries diverge sharply. Okay? If we look at end of the results in 2007, Korea, their per capita GDP is 24,000. This is more than tenfold increase. Philippines, it was only 5,000, just barely, slightly more than twice. What's behind this difference? So look at the growth rate. So Korea, the growth rate was 5.5, this average growth rate. Okay, so this, we are talking about 50 years. And 15, the growth rate is 1.7. If you only compare these two numbers, it seems like not big difference. But then over time, it's making a huge difference. Remember earlier we talked about rule of 70, right? So for South Korea, 5.5%, they're just going to take 70 divided by 5.5, just barely, just a little bit more than a decade to double their income. So you can see, so during the past 50 years, they are going to be able to double their income 3 times. So that's why it ended with their GDP grow more than 10 times. right? But the Philippines is going to take much longer to double, or in other words, the growth is much slower, right? But now finally, the question is why? Why there's divergence? What is behind their story? One is very successful, the other is less so. Okay, so this is something we need to understand. Now we are going to have a solow growth model. The starting point is population growth, right? This population growth, this is a little bit different from Marx-Saucing model. And here, so we assume the population growth at a constant rate, right? So this is given. Remember in Marx-Saucing model, the population growth rate is going to be a function of per capita consumption. Now here we're going to drop that assumption. Why we drop that assumption is because, as you're going to see, there's something more important. There's something more important than population. There's something more important than land. Okay. Before I move to the next slide, I want to emphasize here, N, it is a population. Also, this is an indicator for numbers of workers. Okay, so here just for simplicity, right? We just assume everyone work, right? Okay. Now M prime here, the prime, M prime, this just denotes the value of the next period or next year. That just means, so if today, so the population is N, and then so next period or next year, the population is going to M prime. And N prime is going to equal to 1 plus N times N. So this is a growth rate. Okay. In terms of consumer, this is another difference compared with the Marx-Saucing model. In Marx-Saucing model, so consumer consumption equal to Y, and Y consumption equal to Y in Marx-Saucing model. It's because we were in an agricultural economy. Everything is perishable. If you don't consume, it's going to perish. Okay. Or if you don't consume, it's going to be wasted, right? And then so the optimal choice or rational choice for you is just to consume everything. But now here is different. It's different. Actually, we are entering a post-industry revolutionary era. In a sense, if there's things we left unconsumed, we save, and then so we can convert them into machine, or we can convert them into capital. And this capital is going to be used to build or to expand our production in the future period or in next year. Okay, so this is going to capture by S. S is saving, right? So and then so the rest goes to consumption. Okay, sorry. The S is saving and the rest goes to consumption. But in Marx-Saucing's work, S equals 0 because there's no way for you to save, and there's no point for you to save because in Marx-Saucing's model, so what matters to output or to production is land, and particularly is land per person. Now here, what matters to your production is capital, and then where the capital coming from? Coming from saving. Okay, so that's the key difference. But a certainty, sorry, one more thing. A certainty here, what determine is unknown, or so is given. So is the fraction of the saving rate is exogenous given to the economy, right? And in a later chapter, we are going to have a theory to explain what determines households' saving decision. For now, the saving decision is exogenous given, so it's just given by households. Okay, you can think about there is a government or there's a authority just tells you how much to consume, how much to save, right? Now goes to production side. Okay, so there's a firm. Okay, it's going to produce Y, and in order to produce Y, what they're going to use? They are going to use to N, which is labor, K is capital, and Z, this is technology. Okay. First of all, this Z is exogenous given, right? So actually, this is called the technology level. Okay, this is exogenous given for this model. All right. So in that sense, similar to Marx-Saucing model. Now, the key difference from Marx-Saucing is that the production is going to depend on capital. Right? Yes, they're also depending on labor, right? So both rely on labor. But now, so the production is going to rely on capital. But what's the difference? What's the fundamental difference between capital and the land? Land is fixed. But in general, there's no way you can create new land. Yes, you can explore a little bit, but then the overall acreage on Earth are given. But then, so capital, so you can keep building more and more machineries. You can keep building more and more factories. So that's capital. Again, where capital coming from? So it comes from saving. Actually, it's coming from it's coming up next slide. All right. So this is production. So the production function, it has some very nice property. One is called a constant return to scale. So essentially, it just says, actually, so here, let me just say a few words here. So just k divided by n. Actually, this 1 comes from n divided by n, right? So this 1 divided equal to n divided by n. Or in other words, here on the right-hand side, for k and n, you're going to shrink by the same ratio, which is n. You're going to shrink by same ratio. And then so on the left-hand side, output is going to shrink by the same ratio. Alternatively, if you just grow this by same ratio, say we become x, okay, and then so the output is going to grow by x the same way. So this is called constant return to scale, meaning so you double your resource, double the size of your resource used for production, and then you're going to double the output. You cut your resource by half, and then so your output is going to cut by half. So that's how it works. Now it is constant recurrent. Now, not only so the production function has a constant return to scale, it also have these nice diminishing return to scale. Right? So this is something we have discussed earlier when we study one period closed economic model, right? Here we have K on horizontal line, but remember this is capital per worker. This is K over N, okay? Capital per worker. Vertical line is output per worker. This is Y divided by N, okay? So by the way, let's go back to previous slides. Essentially here, we use Y to denote the Y divided by N. And here we use K, lowercase k, to denote K divided by N. Because this is constant, this term is constant, and then we can ignore. So N always here, right? So you may be wondering why we cares about this lowercase or why we focus on per worker. This is because in order to measure the standard living, it's better to look at per person term or per worker term instead of look at the aggregate, right? Because at the end, the standard living is measured by how much each person can consume, how much each person can produce, how much income each person have, right? So this production function is concave, means the slope is declining. But what's the slope? The slope is giving you the marginal productivity of capital. What is marginal productivity capital? So essentially it just says, so look at how this is how we calculate the slope. This just slope just tells you, so if capital increase by a certain amount, how much does Y increase? By the way, the delta here is usually, there's delta, usually it means the change or difference, okay? The change or difference, right? So the slope just tells you this, like in the margin, how much output will increase if capital increase by a marginal amount, right? And clearly you can see this curve has a flatter and flatter slope. This means these values become smaller and smaller, okay? Or this means marginal productivity of capital is getting smaller and smaller. And finally, it just means, so the more capital you have, the additional unit of capital brings you less and less output increase. This is what this means. But this play a very important role in solo growth model, in understanding many important phenomena as we are going to study. All right. Okay, so now this is the key. So how we are going to understand the evolution of capital, right? So the capital in the next period is going to rely on two sources. Okay. Source number one is going to rely on how much capital you have, right? So this is capital, and then 1 minus d, so that is after. And by the way, so d is the depreciation, right? It's a depreciation, and then so capital. This is what you have from previous period, right? And what is I? I is investment. I is investment. Okay, so the investment it just help you to. It's going to help you to grow your physical capital. So this is how things work, right? Okay, and then so depreciation. So the depreciation, the more you depreciate, and the less you have. So this is how it goes, right? Okay, but again, so this depreciation, the d is exogenous given, right? So this is given as a parameter. Is exogenous given to the model. It's exogenous given to the model. All right. So now we can have overview of this model. And then, so from there, we are going to solve this model or to understand the underlying mechanism of this model. Okay? For this model, so you have the following exogenous variable. S is saving rate. D is depreciation. N is the population growth. Z is technology. So those are given. Those are given exogenous variable. We have some endogenous variable. This is included Y, which is total output. K is capital. N is labor. C is consumption. I is investment. Okay, I is investment. Sorry. So first we have income expenditure identity. So Y equal to C plus I. Remember earlier we talked about measurement of GDP. So we have G, which is government spending. We have net export. Okay, so this is the usual GDP income identity looks like. But now here in this model, so we don't have government, we don't have import and export, so just simplify. So Y equal to C plus I. Now for the households, so by the way, this income expenditure, this is from the economy-wise. But in terms of households, what you can do is C plus S, right? So for each income they have, they either consume or save. Hence, if we combine these two, immediately you're going to get the following: S equal to I, or investment must come from saving. Now we can plug in this S into the law of motion for capital. Right? Let's go back. Or in other words, we use S. Let me erase here. So basically, we are going to combine with two. I equal to S, and S equal to lowercase s times f of k. Right, sorry. Okay, lowercase of k. No, sorry. Erase it. S times 1. Right? So this is, so we are going to plug these two into this equation. Hence, we are going to get this one. Right? So first is equal to I equal to, sorry, first I equal to S, and S equal to S times Y. And then Y equal to Z times F of K. So now we end up with, so K prime on the left hand side equal to K times 1 minus D plus S times Z times F of K. We can rewrite everything in per worker term. Right? So how we are going to do that? So let me erase and then just tell you how we are going to arrive that. Left hand side is K prime. Right side is K. Okay, so now we are going to divide both sides by N. So hence left side is going to become K prime divided by N. And right hand side, so now K divided by N, it becomes lowercase k immediately. And times 1 minus D. So that's given. Okay. And then in second term plus S times D. Okay, but now remember you have a constant return to scale. So the divided by n and outside is equivalent to divided by n inside. So you're going to get f of k. So that's going to, okay, so this is how we are going to get these two terms. Now what happens to the next side, the left-hand side? So for the left-hand side, what we can do is we just do the following manipulation. All right. So now we are going to combine these two. So then it's going to get a k prime. And these two is going to give you 1 plus n, because n prime divided by n equal to, sorry. So 1 plus n prime divided by n equal to 1 plus n. So that's how we end up with this equation. Okay, let me just repeat how we're going to get. Okay, so first take this equation. Take this equation. We're going to divide by n for both sides. Step number 1. And now step number 2, for the right-hand side, capital K divided by n equal to lowercase k. Okay, and f of k, so divided by n becomes this lowercase k. This is the right-hand side. Left-hand side, so you have k prime divided by n, so that's here. Now we are going to times n prime divided by n times, so that's going to keep the value, keep the identity. But then, so we are going to connect these two, k prime divided by n prime. So that's going to define as k prime. And n prime divided by n, that's going to equal to 1 plus n. That's given from the model. So hence, we are going to end up with this equation. All right. So now let's just understand what this means for this equation. So particularly if you move this term to the right-hand side, okay? And then they just says the per capital capital is going to determine by the following 3 things. Number 1, certainly the more you save, the more you have. Number 2, the depreciation, meaning so the more your capital lose its value or lose its functionality, the less capital you're going to have in the future. And number 3, so you move 1 plus n to the right-hand side, is going to become the denominator. And furthermore, that's going to reduce the value when n increase. How do you understand that? That essentially just says the population grows, or the more worker you have, that's going to dilute the capital you have, right? So that's how these 3 parameters is going to affect the evolution of physical capital, and particularly per capital capital. Okay, and here this is just summarized by this equation, this slide. So there are 2 opposing forces driving capital per worker. Number 1 is investment. So consumers save a constant fraction of our income, and this saved income will be used for investment. Certainly that's going to increase the future capital. Okay. But on the other hand, the growth of population and the depreciation of existing capital, that's going to reduce the amount of capital you have, right? So we understand what's depreciation. That just means your capital, just think about you have a phone, it lasts for 5 years, and then over time it's going to gradually lose its value, gradually lose its functionality. And then the growth of population, that just means if we have a fixed amount of capital, and that just means you have more worker to share this given fixed amount of physical capital. So hence you're going to see the dilution of physical capital, right? So this is why the growth of population and the depreciation is going to have a negative impact. But by the way, so there's also a diminishing return of physical capital. That just means for each additional capital stock you have, right? Sorry, each capital you have, okay, and the contribution to Y is going to decrease. Okay, so first you have some capital like investment, but this impact on Y is going to decrease. But in the next period, so this is going to mean S times Y is going to decrease. Right, so this diminishing return, but it's coming in the next slide. Okay, first you look at this diagram. On the horizontal line you have K, the vertical line you have K prime. Meaning, so this is a diagram show you the evolution of physical capital. Just show you how the physical capital change over time, increase or decrease. Okay, so how that change over time. Okay. And then here, so you have 45-degree line. They just help. This is used to help the. This is used to facilitate. This is used to facilitate the analysis. And then this light blue line. So this is just given by this equation. Okay. First, the shape of this line is going to be given by this one. Remember, so a function is a concave, right? And essentially you just multiply some constant in front of f of k, because s times z divided by 1 + n, that's a constant. You multiply it in front of k. Okay, let me just highlight. Let me highlight it here. Okay. So essentially we just multiply this term with f of k. This first. So actually this just tells you the shape. And this term essentially is just like adding a constant to this concave function. Now, because this concave and eventually this curve is getting flatter and flatter, and it's going to flatter than 45-degree line. So that's why eventually this curve is going to cross the 45-degree line. But what is particular about this the cross of this 45-degree line? It just means at this cross, what do we have? We have k prime equal to k. Okay, at this line. But furthermore, this means k prime equal to not only k prime equal to k at this cross, you also have k prime equal to this entire equation. What this means? This means so you have k today. Okay, after depreciation, after saving, so that's going to give you exactly k next year. Or in other words, this means once we are here, and then the economy is going to stay here forever. So that's what this means. But then, so why the economy is going to stay here forever? So that's the question we're coming up soon, right? First, let's see. So what determines this cross, the level of this cross? Okay. Sorry. Yeah. So we need to understand what determines this cross, right? But now, so in order to understand what determines this cross, we can do a simple algebra. So this simple algebra essentially just give you the following, but certainly there's like some approximation. So this approximation just says, okay, so it just says, so it's given by here. So when k prime equal to k, right? Sorry. So it's given by k prime equal to k, okay? And then, so from k prime equal to k, and we end up with here, we end up with this equal to this. Or in other words, when m plus d times k equal to s times z times f of k, so you're going to get k prime equal to k. Okay, this is some simple approximation. But this simple approximation helps us to understand the determination of the long run state of the economy. Also help us to understand the underlying mechanism of this model. Okay, so actually, so these two terms, let's call this one and these two terms is corresponds to different force as we discussed earlier. So this one, let's go back to previous one. One is refers to the investment, and two refers to here. Okay, let's go back. So one, this just refers to investment. Okay, and then the two here, this is just for the population growth and the depreciation. Okay, so that's going to dilute the capital, meaning so this is a positive and meaning this is a negative, right? So when the capital, so yeah, first of all, when we hit here, so that just means that the addition to physical capital exactly offset by the decrease in physical capital, or the decrease in physical capital is going to exactly compensated by increase in physical capital. So they are going to cancel out each other, and hence the economy is going to enter the long run steady state, or in the long run, so the physical capital is not going to change over time. All right. Now let's see what happens if physical capital is very low. The level is very low. If the physical capital level is very low, because by the way, so this is negative and this is positive. And this is the difference is positive, meaning so you are going to gain more physical capital than what you will lose. So hence physical capital is going to grow. If we are here, and you can see, so this is what you can lose, but this is what you're going to gain by additional amount of physical capital you have saved. But because of diminishing return, you can see, so the gap is a negative. So that just push you back. Okay, so that's why, so this is where we are going to stay in the long term. Now we can erase everything. So there are two things. Number one, I just explained to you why we are going to stay here in the long term. When you start with low, you're going to push this side because you're going to have positive effect in terms of if we are here and then there's negative effect, it's going to dominate, meaning so you're going to push back, right? So what's the negative effect? That's going to given by this straight line. The positive effect is given by this curve. Now the curve is going to flatter, so that's why it's going to be below this line. Hence, there's going to negative effects dominate. And on the left-hand side, the positive effect is going to dominate. Hence, so either you're here, it's going to push you back to this direction, or you're here, and it's going to push back in this direction until we reach here. And this is going to cancel with each other. We are going to settle in this dot in the middle. So that's what happens, right? Now just imagine initially, so the economy is in a low K, right? Then the productive capital is going to be very high. Then the stock of capital is going to increase until we reach K star. Right. So this is what happens. This kind of just summarize what we discussed in previous slides. Why does the economy settle down to the steady state? This is because investment exists in diminishing return. That's why when K is low, you're going to have positive effect dominates negative effect. Okay? And once we keep increasing physical capital, and your output is going to increase, and then eventually this positive effect is going to become weaker and weaker. It's going to less than negative effect. So that's why eventually we are going to settle in the middle. All right. From the discussion here so far, it seems like in the long run, the economy is going to settle. What this means? This just means in the long run, the Y is going to stay in the same level. This immediately means in the long run, there's going to have zero growth. It's zero growth. So there are two questions. Question number one, what's the usefulness of this model if there's no growth? And question number two, what are we going to expand? The long run growth. Like say in the United States during the past century, the economies keep growing on average at 2% per year. But this model is going to, based on this model, it seems like in the long run, the growth rate equal to zero. So how do you understand this? Let's start with the first question. Even though this model is going to tell us that eventually we're going to settle at a growth rate of zero, but before we settle at that level, you're going to see there's a transition dynamics, meaning so the economy is going to gradually reach that middle point. And then in the process of reach that middle point, the growth rate is going to be different. This is number one. And number two, yes, this model indeed is silent in terms of long run growth. And here, so D is exogenous given. In order to sustain long run growth, you must have exogenous growth over time. But in the next chapter, we are going to have a theory to endogenize this Z. But for now, yes, it is true. There's no long-run growth. But before we reach this zero growth steady state, the economy is in the transition dynamics. Along this transition dynamics, indeed, you have growth difference. That's the key insight. Right? To summarize, this solow model tells us there's a principle of transition dynamics. The further you below the steady state, the faster you grow. The further you're above steady state, the slower you grow. Or in other words, let's go back to previous slides. Essentially says, so by the way, so this is a long run. This is what happens in the long run. Once you reach here, you have no growth. But this growth model says the further you away from this dot or you go to here, the growth rate is higher. If you go to here, your growth rate is lower, even slow. Not only is lower, actually it's negative. Let's just focus on left-hand side. Okay, let's just focus on left side. Okay, let me repeat it. Okay, erase everything. Okay, so let me repeat. If you're further away from this dot to the left, and then your growth rate is higher. So if you compare this dot versus this dot, okay, and then here, so the growth rate is higher compared to here. It's clear, it is very clear by looking at the difference between this curve and this line. Right, so their gaps is getting narrower and narrower. Why does the gap is getting narrower and narrower? It's because this curve is concave. And what does this mean? What does it mean? The curve is concave. It just says the marginal productivity of capital is diminishing. All right, so this is transition dynamics. Let's go back here. Okay. And from this principle of transition dynamics, we know the difference in growth rate across country as largely reflects how near or far you are from your steady state. The further away from the steady state usually means the poorer you are, and then the higher the growth rate. The closer you are, meaning the richer you are, and then the slower the growth rate. So that's the main prediction of solow growth model. Right. Now let's look at an example. So United States, if it grows at a constant 2% per year for almost a century, but in some sense, this reflects the fact that US is close to its steady state. But here, as we're going to study later, this essentially means Z is growing at 2% per year, or in other words, all the growth coming from Z. But on the other hand, so China, so overall, so their per capita GDP is much lower, or they are much further away from the steady state. They experience rapid growth of more than 8% per year during the period of 1980 to 2010. So this just suggests China is below its steady state, and therefore it's growing much faster based on the principle of transition dynamics, right? Now, in the following few slides, we're going to study what factor change will help us to achieve higher steady state, right? So we talk about a few factors. Let's start with saving rate, ACE. In the steady state, the saving rate rise is going to increase capital per worker. And this is going to increase the level of output. However, it's going to have no effect on the growth rate of aggregate level. Why? Like I said, in the steady state or in the long run, the growth rate is going to be zero. But indeed, it's going to increase the level. Now let's look at it here. So if you have a higher AS, that's going to represent by this line compared to this one, right? So that just says for any level K, so this entire line is going to be higher at a higher level. So you shift up. We shift up, all right? And then so this new saving line is going to cross this line at a higher level. That just tells us higher saving is going to bring you higher capital per capita. Or in other words, that's going to bring you higher GDP per capita or output per capita. Right. Now let's see how an increase in saving rate is going to change. It's going to change the path of output. We start with here. This is some time period T. And if we are in that path, we just keep going. So just there's no growth. But suddenly at period T, there's a increase in saving rate. Okay, and then so it goes back here. Essentially just says we are here, we originally are here, and now we are just going to apply this line, and you can see there's a gap. So if we apply this line, there's no gap, we stay here forever. Now you suddenly shift this line. So you're going to have a gap, which means you're going to push to this direction until we reach this dot. So that's referred to here. So yes, you're going to suddenly you'll increase your level, and eventually you're going to reach the new level of steady state. New level steady state, right? And you may wondering, what is the slope of this line? So the slope of this line is coming from the constant growth of z. If z is fixed, and then so this line should equal to here, right? And then there's another line, it's going to like this, and then so we are going to shift from here to here. That's how the path will look like if there's an increase in S, but if we just stay with zero z, right? To summarize, okay, so you start from here, and eventually you're going to converge to a point here, right? And then so this is the path you're going to follow. And why there's a path like this is because you're going to have a growth. You're going to have a growth in physical capital. And why there's a growth in physical capital is because suddenly there's an increase in saving rate. It's going to dominate the negative effect coming from population growth and the depreciation, right? And here we can also see its impact on the consumption, right? This line crossed with this line. This is what we have discussed. That's going to determine the capital level in the steady state, or what the long run look like for the economy. And this is the output line. The difference between these two lines is going to give you the consumption. Right. Now here in the steady state, the consumption is going to be given by this level. Right? But this is going to implies a interesting question to think about, right? So right now, so now we have a given saving rate, right? So that's the example given, okay, given to the model. And for a given saving rate, you're going to see there's a consumption, or there's a level of consumption in the long run, right? Now, if we just change the saving rate, you're going to have a different consumption level, right? But now the question is, what is the maximum consumption level you can achieve by adjusting S? Okay, and so this is that maximizes the level of C in the long run. Usually we call it golden rate of saving, right? Okay. And here, so this is a golden rate of saving, how this looks like, right? Essentially, so we are going to change on the horizontal lines, change the capital stock. It's going to change the capital stock. But then this change in capital stock is caused by change in S. Or in other words, on the horizontal line, we are going to adjust in S from zero, let me see. So from the horizontal line, so we are going to change saving rate from, yes, I think it's zero, yeah. So because you have zero saving rate, and then so the economy is going to produce nothing in the long run, right? Okay, so you continue to change S. For each S, you're going to have a different steady state capital stock, right? This is what happened on the horizontal line. But then, so for each different capital stock, it's going to, and plus this, there's a S associated with this capital stock in the long run. That's going to imply a consumption level, right? Because the consumption level is going to is given by the difference. It's going to be given by the difference between your output and your saving function, right? But remember, so if you adjust saving, like significantly adjust saving, and then you're going to have a line that like here. So that's the difference. If you're higher saving, you're going to go to here, right? And at the same time, you're going to adjust. You're going to adjust this line. So you're going to, this is the consumption. Maybe let's erase everything. Okay, so what I'm trying to say is, so here, this is a particular saving rate. Now, if you increase the saving rate, first you're going to have, if you increase the saving rate, so first you're going to have something like this. This is the saving function. Okay, so this is number one. Now the capital is going to increase, okay, and then so this line, remember this line is for a steady state K. So that just means you're going to go to here, this output. So now we are going to look at the difference. All right, so you can see the difference. So in other words, the difference in or the consumption is going to vary with the level of saving you choose. But then, so this line just this graph just tells you there is a particular saving rate that's going to maximize consumption in steady state. And this saving rate that maximizes consumption in steady state is called a golden rate of saving. All right. Now we look at another factors. Just imagine if there's a change in population growth. Okay. And similarly, so there's going to be no effect on the growth rate of aggregate variable, but it's going to have impact on the level of capital in the steady state. So this is how it looks like. So if you increase n from n1 to n2, and then this line becomes steeper, move to the left-hand side. Now you're going to cross this line. You're going to cross this line at a lower level. This just means the higher population growth is going to push down the physical capital. It's going to push down in the physical capital, right? And the intuition is simple. It's because if you keep everything else fixed, the higher population growth, meaning there are more workers. More workers must share the fixed amount of physical capital. Hence, you are going to have less capital, or you can accumulate less capital over time, right? So based on the prediction, based on those discussion we have two predictions of the solow growth model. Number one, richer country must have a higher saving rate, or high saving rate usually leads to higher growth, or higher steady state physical capital and higher income. On the other hand, lower population growth usually means higher steady state physical capital and output. All right. Now we can look at the actual data and see so how that change over time, right? So this is US on the horizontal line is investment as percentage of output. On the vertical line is the real income per capita as a percentage of US GDP. Actually, sorry, so this is for different countries. So we should look at worldwide. For each country, on the horizontal line, we just plot the country's investment rate. On the vertical line, just plot the country's real income per capita compared with United States or normalized with United States. And clearly, it shouldn't be too difficult to see there's a trend, like a positive trend, right? Meaning, so the higher saving rate you have, and then higher income you can sustain in the long run. Now, on the other hand, so we can look at how population growth rate matters to your real income per capita, right? Similarly, vertical line is just real income per capita normalized by US per capita GDP. On the horizontal line, it's population growth for each country. And clearly you can see there's a negative correlation. Or in other words, higher population growth, holding everything else constant, implies lower real income per capita in the long run. Okay. So now we can go back to the case study or the motivating example, we have look at the beginning. So this is South Korea and the Philippines. We knew what happened for these two countries between 1960 and 2007. And particularly, we find out their growth rate is different. It end up with their per capita income is dramatically different. But what is behind their difference? Now, based on the solow growth model, so we should have a good answer for that. So now first look at the data. This is the time period from 1950 to 2000 and their investment rate, right? So this is the United States in the middle. This is Philippines, this is South Korea. And clearly South Korea has a much higher saving rate. And based on the solow growth model we have just discussed, higher saving rate implies higher growth in the short run, and in the long run, it's going to imply much higher per capita capital and per capita GDP. So essentially, so you're going to move up the curve that cross with the line, right? So that's what we discussed earlier. Now, we are going to shift to the source of long-term growth. And clearly, this is not, we cannot rely on saving, right? For two reasons. Number one, it must always be below zero. You cannot exceed one, right? And secondly, so once you hit the limit, you're going to reach, eventually you're going to reach to your long-term level of physical capital and long-term level of income. So hence, saving rate is not going to be the answer to long-term growth. Now, what about population growth? Similar to increase in saving, right? So you cannot keep decreasing population, right? So actually, if you decrease your population in the short term, yes, it's going to help with your economic growth or increase in income or increase in physical capital. But it also has a negative impact because smaller population, it can end up with lower level of innovation, right? But anyway, so this just means from this slide just says neither saving rate change or decrease in population size is going to bring you long-term economic growth. But then what is source? The answer lies on Z. So if we can manage to increase Z constantly or in a sustainable fashion, and then so we can sustain increase in per capita income without any limit. But again, so the question is how we can increase Z. And so we must wait for the next chapter to understand the source of Z increase. But for now, so the main message is in order to reach long-term growth, you must keep Z growing continuously. All right, but then the question remains is, so how we can make Z grow? This graph tells you if we manage to keep growing Z, right? So first we reach this steady state. Now we are going to move to a higher Z, and then so you'll move from here to here. And then so you have another Z increase, then you're going to move from here to here. Right, so just keep growing. So that's only source of long-term growth. But where Z growth coming from? This is a bit silent. Or this solow growth model is silent on the source of Z growth. Right. To summarize, the solow model is a breakthrough in understanding economic growth. It is very different from Marx-Saucing model, right? The strength of this model is that it provides theory that determines how rich a country is in the long run, right? Its principal transition dynamics allows us to understand the difference in the growth experience across country over time. Right? So this is the strength. Now, what is the weakness? Their weaknesses are the following. First, it focuses on investment and capital. Right? However, the much more important factor of TFP is remain largely unexplained, or it still is like a mystery to us. And secondly, it doesn't explain why different countries has different investment and productivity rate. So those are exogenous given. You don't know why South Korea has higher saving rate compared with Philippines. You don't know why United States has higher TFP growth or higher level of Z compared to the rest of the world, right? And the third, it doesn't provide a series of sustained long-run economic growth. It must rely on some exogenous or mysterious change in Z. Okay, so those are the weaknesses. But nevertheless, this is the first and very firmly breakthrough in terms of understanding economic growth. All right. And finally, so this model has a strong implication. It's called a convergence. This convergence says if two countries are initially rich or poor, they're different in terms of their physical capital and different in terms of their income level, but they are identical in all other aspects. They will eventually reach to the same level of physical capital and same level per capita income. And furthermore, they're going to reach the same level of rate of growth, meaning zero growth rate. So if everything else are the same, right? The difference is going to be the difference in their income level is going to be explained by difference in the following 4 parameters as we introduced at the beginning. Okay? And the difference in growth rate is going to be explained by transition dynamics, essentially how far you are away from the steady state, and also difference in growth rate of this unexplained factor. To summarize, so the convergence says eventually if two countries are identical except income and physical capital level at the beginning, and they are identical to other aspects, including saving rate, including population growth rate, including depreciation, including TFP, if two countries are identical in those dimensions, and hence in the long run these two will converge, or this two is going to reach the same level of physical capital, is going to reach the same level of per capita income, right? And then the growth difference between two countries is most explained by 2 things. Number one, they are different in growth rate of TFP. Number two, they may be in a different level in this transition dynamics, right? So this is the convergence, right? So we have a few practice questions. So I'm going to have a separate discussion for those practice questions for us to understand. For now, let's just finish the main content of these slides. Right, so now let me just look at gross accounting, right? So what is gross accounting? Gross accounting is based on solow growth model. We use this solow growth model to measuring or to understand the impact of aggregate input on output, right? So from there, we are going to understand the contribution of each factor input on the growth of output. And furthermore, from this growth accounting, we also can have a sense what is a total factor productivity growth, or in other words, we are going to have a measure of Z growth. So this is the main point of growth accounting. Now let's look at some functions so that we can understand how the growth accounting is conducted. We start with this production function. Right? Y is the total output. It's going to depend on K and N. But now we also have a Z. I should put a Z here. Apologize. There should be a Z here. Right? And then the output is going to depend on Z, which is the TFP, capital, and the labor. So this will depend on these 3 factors. And here there's our alpha as a superscript for K, and then 1 minus alpha for superscript of N. So this alpha and 1 minus alpha, as we are going to see later, essentially is going to present, or is going to indicate the contribution of each factors. Right? Now let's look at example. Right? If you have alpha equals 0.36, that just means the 1 minus alpha equals 0.64, right? Or in other words, so this is how the production function looks like. But you were wondering, so where we come up this number? This 0.64 actually coming from the labor share of national income. How we understand that? So this is essentially just says, okay, so for you to produce, you use two sources. One is use K, another use N. Okay. And you use this resource, and then so you must have some compensation. You have some compensation to each factor. Similarly for K. Okay. And this some compensation is going to show up as income. Okay. So, but the income is close to households, right? And then so actually, so both income is add both income together, you're going to get Y. Okay. But now, so if you look at income, that goes to compensate your labor input and divided by this total income. Okay, so that's essentially to tell us so the contribution of labor supply in producing the final output. And then so we use this share or we use this ratio plug into here. So that's how we end up with here, right? And from this equation, we can do some algebra, and then we have z equal to y divided by this term, right? Or in other words, so this z is going to measuring everything else that cannot be explained by capital and the labor input. Remember, so y, in order to produce y, you have three sources, k, n, and then z. So you use y divided by these two terms, the product of these two terms. That just means everything else goes to something else, which is z. So that's how we define z. And z actually is called solow residual. Actually, economists call this is a measurement of our ignorance. And why is a measurement of ignorance? Is because so we only observe y, which is the total output. We observe k, which is the capital. We observe labor supply. But there's something unobservable. What we knew is important to produce y, which we classify as z, and this is how we back out. That's how we back out the z. This is how the z looks like for the U.S. economy, and overall this is increasing, but there's like fluctuation. Right, and here so we have taken natural log for this residual, but easier for presentation. Okay. Now we are going to do some growth accounting. First, we look at average annual growth rate for the U.S. economy. So this is a number we come up. So just for each decade. So essentially, we just calculate y(t) plus 1 divided by yt minus 1. Okay, so this is just a percentage change. This percentage change. Sorry. Okay, this percentage change. All right. And here, so this is solow residual, but then the solow residual is just deviate from the trend. Right. So this is solow residuals in the middle. Right. So just so it's just percentage change. Right. And here, so this GDP also this is a percentage change compared to the trend. Now it goes to the center part of growth accounting, right? For the growth accounting, so we can do the following, right? So we are going to get these equations. The way we get this equation essentially is we're going to take log. So remember, we start with y equal to z times k 0.36 times n 0.64. Okay, and then we are going to take a log. Okay, and then once we take a log, and then so we can come up with this difference, right? So if you, so I won't cover these mathematical details. So if you understand this is good enough. So just keep in mind on the left hand side, this is the growth rate. Right, this is a growth rate. Let me erase everything. Make sure. So I guess so you understand the economic intuition. That's good enough for now. Okay. So on the left-hand side, this is the growth rate of GDP. So delta means change. So change in GDP divided by the GDP that is growth, those growth rate. And here, so this is similar. This is the growth rate of TFP. So now this is the growth rate of physical capital. This is the growth rate of labor supply. Now this is alpha, and this is 1 minus alpha. Remember how we get alpha and 1 minus alpha. So essentially, is their share or is their contribution to the output, right? So that's just coming from data. Okay. Now from this equation, now we understand this equation. So the equation just essentially says the output growth is coming from three sources. You can grow your output by increasing physical capital, or you can grow your output by increasing the size of your labor force. Remember, this is aggregate, okay? And finally, you have some other source, but we don't know, but we kind of can implicitly or indirectly measure, which is TFP. So these three sources of growth is going to add up with total observed income increase. Okay, so this growth, this is how we do the decomposition. So you observe a growth in income, right, or total GDP, and these can decompose in these 1, 2, and 3 sources. Okay, so this is the first step. Now in the second step, so once we come up with each numbers, maybe go to the next slides. Okay, so first, this is how we are going to come up with GDP, capital, employment, and the social residual. So we can observe this data. So actually, this is just total GDP. This is total GDP. We also can observe this data. This is the total amount of physical capital, machinery, buildings, so on and so forth we have in the economy. And finally, we can also observe this, which is this is going to be the labor supply, right? And then, so we are going to use the equation we have discussed earlier. So essentially, Z is going to be using Y divided by K raised to the power of alpha times N raised to the power of 1 minus alpha. From there, we are going to cover the value of Z. But again, we do not directly observe Z, but we can, based on the observation of total GDP, the observation of physical capital, the observation of total labor supply, plus the equation we have discussed earlier, which is a production function, to recover Z. Okay, so this is the first step. Now, from the observed Y, K, and N, and also the implied Z, we can calculate the growth rate. So this is a growth rate for each decade. So for example, so how we understand that? During 1950s, during that decade, the growth rate of total GDP is around 3.5%. And then we have 3.7% of growth in capital and 1.1% growth in labor supply. And then there's a 1.42% growth in technology or TFP. Now, the last question is, so we are trying to understand what is the contribution of the capital accumulation on the observed output growth? What is the contribution of labor supply growth on the observed income growth here? And finally, what is the contribution of this technology growth on the observed output growth, right? And so the way we do that, let's just go back to the previous slides. So remember, we have this equation, right? So this must hold true. What this means is, see, the output growth partly coming from capital growth, partly coming from labor growth, and then the rest goes to the TFP growth. In order to compute their contribution, so for example, if you're interested in the contribution of, capital growth, and then so what we're going to do is, so for example, you have, let's call it like a GK, okay, so here's GK, and here you have GY. By the way, so GK just equal to this number, and GY equal to this number, right? And then the contribution of capital growth to output growth is going to equal to 0.36 times GK divided by GY. So this is how we calculate the contribution of capital growth. And similarly, if you're interested in the labor growth, its contribution on output growth, and then we are going to use 0.64 times G of L divided by G of Y. Again, so what is GL? GL is the growth rate of labor. And then lastly, so we can use GZ divided by GY to calculate the contribution of Z on the income growth. Right, so this is how we decompose. This is how we decompose the contribution of each factor. Remember, there are three factors. Factor number one, which is capital accumulation. Factor two, which is labor growth. Factor three, this is technology, which is unobserved for us. And then by doing this, essentially, there are two steps, maybe three steps. Step number one, let me summarize. Step number one, we get the data on Y. Let me write down. Step number one, we get data. Okay, so data on Y, on K, and on N. From this data, we are going to recover the value of Z. This is step number one. Step number two, we are going to calculate growth rate, right? So hence here we have GY, we have GK, we have GN, and GZ. Okay, so we are going to calculate the growth rate. Step number two. Step number three, and then so you are going to use these things to calculate their contribution, the contribution of each factors, right? And then so their contributions add up together. So that's kind of that's kind of tell us which one is more important, which one play a bigger role. Now let's go back to here. So this is kind of a case study. Right? Let's look at one particular country, so Singapore. So if we look at Singapore in 1960 to 1990, so we can calculate their output growth. We calculate the capital growth, their labor growth. And finally, we calculate the TFP growth, right? And then, so by using the equation we have discussed earlier, and even I brought this number, and clearly you can see, so the TFP growth play a very small role, particularly compared to capital. This is for Singapore. Now, if you look at other region or other economy, so for example, Taiwan, now clearly you can see the TFP play a much bigger role compared to at least Singapore, right? So that's the difference. That's the value of this gross accounting. To summarize, what's gross accounting? Gross accounting is, so we observe some growth, output growth. We are trying to understand, so what is the contribution of each factor? This is including capital, this is including labor, and this is including TFP. By using this gross accounting, we can understand the contribution of each one of those three factors, their contribution to the observed output. All right, so that is the solow growth model and the gross accounting. Okay, so in the future, we are going to have a review session to discuss some practice questions to further consolidate our understanding regarding the solow growth model and a more sourcing model.